Hello everyone! Today we're going to talk about linear algebra. And I'm Chrissy Kim. So, linear algebra, what is it? What is so important about linear algebra? Linear algebra is vital in multiple areas of science in general. Because linear equations are so easy to solve, practically every area of modern science contains models where equations are approximated by linear equations. And solving for the system helps a theory develop. More specifically, in mathematics, linear algebra has its use in abstract algebra. Vector spaces arise in many different areas of algebra, such as ring theory, module theory, representation theory, Galois theory. Wait, am I pronouncing that right?
Galois theory.
Oh, never mind then. Anyways, understanding the tools of linear algebra gives one the ability to understand those theories better, and some theorems of linear algebra require also an understanding of those theories. So everything are linked in many different intrinsic ways. Here are some real-world relationships that are governed by linear equations and some of its application. Load and displacement in structures, compatibility in structures, finite element analysis, mechanical vibrations, control theory, machine learning, and so on. Interestingly enough, large problems of these types listed here can be converted into simple matrix equations, and most of these equations are of the form So let's understand how linear algebra came to be. What's the meaning of linear? The word linear is to be understood as in a linear function, g of x equals mx plus n, where m and n are numbers. If you've studied calculus like I did, then you would know the Taylor expansion of a function f is f of x equals this list of equation that goes on and on. What we do here, however, is to use only the first two terms of the Taylor expansion of f, and that would give us only this part that is underlined, and this would give us a linear approximation to our function f. If we rewrite this equation, then we could write this in another form like this. And you can see that this is a linear function, just like g of x. I told you previously, g of x equals mx plus n. So here we can notice that f prime of x of 0 would equal m, and this guy over here would equal n, which is the constant term. This approximation works pretty well. How linear algebra comes in, though, is a little bit tricky. Suppose what we would do if we have a function that depends on several variables. This is called multivariate calculus because it's multivariables. In this case, f prime of x of 0 becomes a vector that has to be multiplied with the vector x minus x of 0. M and n will become vectors too. F double prime of x of 0 becomes a matrix that has to be multiplied twice with the vector x minus x of 0. This is how linear algebra kicks in. Simply saying, linear algebra is your ticket to multi-dimensional space, such as the three-dimensional space we inhabit, or the space of many variables a function depends on. Now let's talk about examples in real life. Economics example. Price depends on supply and demand. So price would be our function f, and supply and demand are the two components of the two-dimensional vector x. So if you do economics, you do linear algebra. The next example is politics. If more roads are built, capacity goes up. That would be good for business, but quality of life goes down. People move away, which results in more traffic, which leads to less excess capacity, which is bad for business overall. Many variables and complex connections lead to multivariate calculus. Last but not least, physics example. If you don't watch a moving car from the outside, but sit in the car, you're changing your frame of reference. This corresponds to a change of basis in linear algebra, which naturally pops out the centrifugal force from your force expression. And yeah, that's the simple definition of a linear algebra and how it is used in real life. I hope this video made sense to you and motivated you to learn deeper about linear algebra. Thank you!